Hi everyone, my name is Jiun Cai Ong from Technical University of Denmark, and today I'll be talking about large-eddy simulation of n-dodecane spray flame, particularly focusing on the effects of nozzle diameters on autoignition at varying ambient temperatures. The content for today's talk is as such. We'll start with a brief background and the aim of the study, followed by numerical setup and operating conditions. Next, we'll look at the results for the non-reacting spray and the reacting spray. Lastly, we'll go to some conclusions and acknowledgements. Now let's start with the background. Below is a figure for the initial delay time of n-dodecane spray from two nozzle sizes, 90 and 160 micrometer in a constant volume chamber. The ambient conditions are given as such: 15% O2, 22.8 density. Ambient temperature varies from 800 to 1000. One would notice is that when you decrease the ambient temperature from 1000 to 800, you'll notice that the initial delay time between the two nozzle sizes actually increases. So as you can see from here, you'll see that the initial delay time between the two nozzle sizes are very small. But as you go to 800 Kelvin, the difference between the initial delay time, the difference of initial delay time between the two nozzle sizes have increased. So this is actually the aim of the study, which is to investigate the effects of ambient temperature as well as the nozzle diameter on the spray ignition characteristics. Now let's look at the numerical setup and operating conditions. So for the turbulence model, we are using LES and dynamic K equation. For the chemical mechanisms, we are using a reduced n-dodecane mechanism developed by Yao, reference given at the bottom. For the combustion model, we are using partially stirred reactor coupled with CCM, where CCM stands for Chemistry Coordinate Mapping, developed by Mehdi Jangi. So how does CCM works is that it is mapping the physical domain into a low dimensional phase space with few thermodynamic variables as independent variables. So in this case, the phase space, we are assuming a 4-dimensional phase space based on temperature, local equivalence ratio, scalar dissipation rate, and the mass fraction of field. And by solving the phase space, we are able to speed up the calculation of chemistry rates. And for the injector information parameters, the nozzle diameter we are looking at is 90 and 186, which corresponds to ECN's spray A and spray D. And for the oxygen level is 15%, density is 22.8, and ambient temperature we are looking at 800, 900, and 1000. First, let's look at the non-reacting spray result. So for non-reacting spray, we know that for the ambient oxygen content is set to 0%. So as you can see right here, and the mesh size we are using is 0.125. The time step we are using is 25. And in a non-reacting spray, we are actually validating the vapor penetration length as well as the liquid penetration length. So we are actually comparing for spray A and spray D as well. We are considering spray A and spray D as well. So the two nozzle sizes. And from the results, we can see that we actually have a good agreement with the measured penetration length. So after looking at the non-reacting spray, we'll look at the reacting spray. So for the reacting spray, our oxygen level now is 15%, whereas for other conditions or other parameters, we keep it as the same as the non-reacting condition as presented previously. So the diagram on the left is the initial delay time versus the ambient temperature. The lines are the measurements, the symbols are the simulation. And we actually get a very good agreement with the experimental data with a maximum relative difference of 14%. In addition to that, our simulated initial delay time actually captures the trend where in IDT between spray A and spray D increases as ambient temperature decreases. So as you can see, the two dots are there's quite negligible difference at 1000, but at 800 Kelvin you'll see that they are significantly different. So which is similarly captured for the experimental data. And one thing to take note is that at the low temperature regions, at 800 Kelvin, we are over predicted. This is likely due to the simplification of the low temperature oxidation in the Yao mechanism. So in order to explain or understand why this happens, or why we observe this phenomenon, we actually plotted out the mass fraction of OH versus the scalar dissipation rate as given on the figure on the right. So we did for spray A and spray D for 800 Kelvin and 1000 Kelvin. So one would notice is that the scalar dissipation rate for spray D at 800 Kelvin is higher by a factor of 5 compared to spray A. Okay, but if you look at 1000 Kelvin, you'll see that the scalar dissipation rates between spray A and spray D are very similar to one another. So this actually, it is known that when you have a high scalar dissipation rate, you have a longer ignition delay time. Therefore, since there's a difference in scalar dissipation rate between spray A and spray D at 800 Kelvin, therefore you will observe a difference in ignition delay time at 800. When at 1000, because the scalar dissipation rates are similar, therefore you will get very close or sort of similar ignition delay time at 1000 Kelvin. So besides looking just at the ignition delay time, it is also worth looking at the ignition location as well. So let's consider a reacting spray case at 15% O2, 22.8 density and 900 Kelvin. And the left one is for spray A and the right one is for spray D. And one thing we'll notice is something called delta T. So delta T is just the change in temperature, which is equals to the local temperature minus the ambient temperature. And particularly for this case, obviously it is 900 Kelvin. So let's look at spray A, the video for spray A. And now let's look at the video for spray D. One obvious difference that we can see is that for spray A, the ignition happens at the head, whereas for spray D, it actually happens at the spray peripheral, which is at the side. The observation in our simulation actually agrees with or actually corresponds with the experimental observation obtained by Pasteur. So, which is shown on the top right figure. The top right figure is actually an image captured by looking at the axial direction of the spray. So this is looking from the side. So if you look from the axial direction, this is what you see. So this image from the experiment is actually obtained from a broadband luminosity image. And if we were to plot out the mass fraction of OH from our simulation, this is what we get. And we can actually see that large amount of OH or a large amount of ignition sites are actually occurring at the spray peripheral rather than at the spray head. This ignition characteristic is similarly observed at 1000 Kelvin. So as you can see from the right figure, this is top is spray A, bottom is spray B. Okay, and you'll see that for the orange region is the sort of like the change in temperature. So you'll see that the orange region for spray A is at the head, whereas the orange region, the ignition high temperature region, you could say, is at the side of the spray or spray periphery. This is not the case when you go to low temperatures. So at low temperature, you'll see that for spray A, it occurs at the head, still at the head. But for spray D, it occurs more at the sort of like a volumetric ignition throughout the whole spray. Then it comes the question to why the ignition occurs at the spray periphery when ambient temperature is larger than 900 Kelvin. So what we did is that we focused mainly on just 1000 Kelvin as it is the most significant difference. As you can see, the most significant difference between them, spray A and spray D. And we'll see that, and what we did was we split the spray region into two parts, which is the inner core region and the outer core region. And how do we split it? By a radius r, which is assumed to be equals to 10 times the nozzle diameter. And this is roughly how it would look like. So the green region corresponds to the inner core, the blue region corresponds to the outer core. So this is for spray A, this is for spray D. Next, we actually plot the scatter plots for temperature versus axial distance for the inner core as well as the outer core. So for this, the top row is for the inner core, the bottom row is for the outer core. And besides just plotting the scatter plots, we actually colored them differently based on the mixture fraction, which is denoted by Z. So if you have a mixture fraction which is less than 0.1, it's given by black. If the mixture fraction is between 0.1 to 0.2, it is red. If it is blue, it is 0.2 to 0.3. Green is more than 0.3. So from here, so first let's look at spray A. So for spray A, we can see that the inner core and outer core have mixture fraction less than 0.2, in which their temperature actually can go up to 1400. So as you can see right here. But for spray D, you will actually see that the inner core has a mixture fraction of more than 0.2, while the outer core has a mixture fraction less than 0.2. So the inner core is actually very fuel rich, and the outer core is more or less fuel rich compared to the inner core. And if you look at the regions where the temperature is more than 1400, they are actually, you will see that the mixture fractions that are less than 0.2 have temperature more than 1400. So this implies that the outer core actually attains a higher temperature than the inner core. So yeah, so one explanation, the main explanation would be the inner core for spray D is more fuel rich, therefore is less variable. This makes sense. This can be explained or attributed to a few DNA studies done by the references given below, where it could be that the cool flame takes a longer time to reach the most fuel rich mixture. In addition to that, the fuel rich mixture itself takes a longer time to have spontaneous ignition due to having longer ignition delay time. So due to these two effects, it causes the inner core of spray D, which is more fuel rich, to be less favorable for ignition to happen. And here this comes to the conclusion of the presentation. So at low ambient temperature at 800 Kelvin, we know that for a large nozzle diameter, we have a higher steady distribution rate, thus leading to a longer ignition delay time compared to the small nozzle diameter. And as for high ambient temperature conditions, one notable difference is that for the large nozzle diameter, you actually have a rich inner core. And due to that richer inner core, it actually causes the ignition to happen at the spray periphery rather than at the spray head in the small nozzle diameter case. And before I end, I would like to say some acknowledgements is that this work is funded by DFF, which is an independent research fund Denmark, as well as Man Energy Solutions. And that's all for my presentation. Thank you very much.